Welcome to this explainer. We're jumping right into the fundamental building blocks of the universe today. Whether you're looking up at the night sky, staring at the screen right in front of you, or just looking at your own hands, absolutely everything around us is made of matter. And today, we are going to decode the incredible hidden language of that matter.
So, here's our game plan. We'll start with the building blocks of matter, peek at the anatomy of an atom, decode the periodic table, compare metals and nonmetals, and wrap up with the awesome power of alloys. Basically, we're going from the absolute tiniest, invisible particles in existence, all the way up to the heavy-duty materials we use every single day in the macro world. All right, Section 1, the building blocks of matter. Let's start at the very foundation of reality itself.
It's a pretty profound question, right? If you take literally any substance in the world and just keep breaking it down, dividing it over and over again, do you eventually hit a wall? Is there a point where you simply cannot break it down any further into something simpler? The short answer, absolutely yes.
That unbreakable wall is what we call an element. It's the simplest, pure substance out there. You can't break it down any further through ordinary chemical changes. We're talking about the classics here, things like hydrogen, oxygen, iron, or gold. But you know what's truly mind-blowing? Think about the sheer massive scale of our universe. Out of all that boundless variety in the cosmos, there are only about 118 known elements that make up the whole shebang. And it gets crazier. Only 92 of those occur naturally. Just 92 natural ingredients make up the entire recipe of our physical world. Moving right along to Section 2, Anatomy of an Atom. Let's zoom way in and see how these smallest particles are actually built on a microscopic level. Think of an atom as the universe's ultimate, irreducible Lego brick. If you've got a solid chunk of gold, the smallest possible piece of that chunk that still acts, looks, and chemically behaves like gold is a single gold atom. It is the absolute fundamental unit of an element. But how do we actually tell one element's atom apart from another?
Well, it all comes down to the atomic number, which you'll usually see represented by the letter Z. An element's entire identity is completely dictated by its number of protons, which hang out right in the center, the nucleus of the atom. Hydrogen has exactly 1 proton, so its atomic number is 1. Carbon has 6 protons, so atomic number 6. Oxygen is 8. That proton count is literally the ultimate ID badge for an element. Oh, and here's a neat little balancing act for you. In a completely neutral atom, the number of positively charged protons perfectly equals the number of negatively charged electrons.
And this perfectly illustrates the really simple math of matter. The mass number is just the total count of the heavy particles crammed inside that nucleus, so the protons plus the neutrons. Let's take carbon again. We already know its atomic number is 6, meaning it has 6 protons. Since it also happens to have 6 neutrons in its nucleus, you just add them together. 6 plus 6 gives carbon a mass number of 12. It really is that straightforward.
Okay, now that we know what atoms and elements are, we need a way to organize all this microscopic chaos. Welcome to Section 3, Decoding the Periodic Table.
You've definitely seen this chart hanging in a science classroom somewhere, but it is way more than just a random list of chemicals. It is a brilliantly systematic organizational tool. The elements are perfectly arranged in increasing order of their atomic numbers, starting at 1 and just counting up. This precise setup is exactly what lets scientists easily predict and study the properties of any element, even the ones they haven't physically interacted with yet. Navigating this map is actually a breeze once you know the secret. It's built on a simple grid. Going across horizontally from left to right, we have 7 rows, and we call those periods. Coming down vertically from top to bottom, we have 18 columns, called groups. Seriously, just remember, rows are periods, columns are groups, and you've basically cracked the code. Let's think a bit more about those horizontal rows, the periods. You'll notice they actually expand as you move further down. The very first period is literally called the short period because it only has 2 elements, hydrogen and helium. The second and third periods expand a bit to hold 8 elements each. That's where we meet familiar faces like carbon, nitrogen, and oxygen. But by the time we hit the 4th and 5th periods, things really widen out. Those are the long periods, packing in 18 elements each. Let's do a quick scan of the first 18 elements, all perfectly ordered by their atomic numbers. Really, you can think of these as the foundational vocabulary of the universe. We kick off with hydrogen at atomic number 1, helium at 2, all the way down the line to argon at 18. Each one gets a specific, capitalized symbol, like O for oxygen or Na for sodium. It acts as this perfect, universal chemical shorthand. Now back to those vertical columns we talked about earlier, the groups. Elements hanging out in the same column actually belong to specific families, and just like real families, they share very similar chemical personalities and traits. Group 1 features the highly reactive alkali metals. Group 2, the alkaline earth metals. Skip way over to the other side, and Group 17 is the halogens. Right next to Group 18, the noble gases, which are famous for being incredibly stable and pretty much unreactive. Basically, being in the same group means they behave in highly similar ways.
Let's pull back from the microscopic side of things and jump to Section 4, metals versus nonmetals, and how they behave in the macro world.
When we look at these elements in our everyday, tangible world, the contrast is completely stark. Metals are shiny, incredibly tough, and fantastic conductors of both heat and electricity. They're also malleable and ductile, meaning you can hammer them flat or stretch them into thin wires without them snapping. Nonmetals? Literally the exact opposite. They are dull, brittle, terrible conductors, and there is absolutely no way you're hammering them out or stretching them into wires. These clashing properties dictate exactly how we can interact with and manipulate different materials.
And that has massive practical implications for your daily life. Because metals like iron, copper, and aluminum are so strong and conductive, we use them for the heavy lifting, building skyscrapers, manufacturing vehicles, and running electrical wires right through our homes. Meanwhile, we completely rely on nonmetals like oxygen for the very act of breathing, nitrogen to create agricultural fertilizers, and sulfur to strike a match. When you think about it, you literally drive in a metal car to go buy non-metal fertilizer for your garden.
But what happens when pure elements just aren't quite strong enough for what we need to build? That brings us to our final section, the power of alloys.
All right, let's talk about what I like to call the ultimate chemical cheat codes, alloys. An alloy is simply a mixture of two or more elements, where at least one of those ingredients has to be a metal. Why do we even bother mixing them? Well, pure metals can sometimes be a bit too soft or prone to rusting. By blending elements together, we engineer materials that are wildly stronger and far more durable than the pure metals could ever be on their own.
By tweaking these simple elemental recipes, humanity forged materials that completely transformed our entire civilization. Take pure copper. It's relatively soft. But mix it with some zinc, boom, you get brass. Mix copper with tin, and you create bronze, a metal so tough and revolutionary it literally got a whole era of human history named after it. But the real game changer? Take iron, mix in just a tiny bit of the non-metal carbon, and you get steel. Steel is what allows us to build massive suspension bridges and towering skyscrapers. It's the absolute backbone of the modern world, all made possible just by mixing and matching off the periodic table.
So as we wrap up this explainer, I've got a question for you. Based on the properties we've dug into today, what elements or alloys are you interacting with right this exact second? Take a quick look around your room. Is there steel holding up your desk? Copper wire powering your screen? Oxygen filling your lungs? Put your new knowledge to the test. The universe isn't just a bunch of random stuff. It's a beautifully organized, predictable system. Start looking for that invisible atomic map hiding in plain sight all around you. Keep questioning, keep observing, and I'll catch you in the next one.